Go.
My name is Michael Newton. My partner is Teaff. For our pop culture project, we decided to take a clip from the movie Taken with Liam Neeson and try to prove it to see if it was capable of happening in the actual real world. In the movie, Liam Neeson's character, Brian Mills, is chasing after the Albanian mob to rescue his daughter from a life of human trafficking. In the scene, Brian Mills jumps off of a bridge and rolls safely onto the boat. After disarming one of the members of the Albanian mob, he starts to walk with a bit of a limp. When they cut to the next scene, he is walking as if nothing has happened. I believe that he would at least have a sprained ankle or something, so we want to do some calculations to see if this was actually true.
Hi, I'm Zach. I'm doing calculations today. Now, in the movie Taken, we did the bridge scene where Liam Neeson jumps off a bridge, lands on the boat, rolls, fights off one mobster, and then walks off like nothing happened. Well, actually came off with a little bit of limp, then walked off like nothing happened. So we want to prove that this was wrong. So first, we had to have a few constants guessed, and we've estimated that the height from the bridge to the boat was about 30 feet, which equals 9.144 meters. Liam Neeson's mass we looked up to be 96 kilograms. His acceleration due to gravity is 9.81 meters per second, as it always would be. And we figured that it would be 0.4 seconds, not 0.9 seconds, change in time. So first we need to find out his final velocity. So we use this equation, final velocity squared equals v naught squared plus 2ax. So let's just fill in the numbers. 0 because he had an initial speed of 0 because he was starting from a standstill. 2 times 9.8 times delta x, which is the height of 9.144 meters. Now we plugged this into our calculator and found out that v final squared was equal to 199.3392. Take the square root of that, and we found that. So we found our final. Oh, that's meters. We take the square root of both. Found that our final velocity was 14.11 meters per second. Now, the velocity of what he hits with isn't what's going to hurt him. What's going to hurt him is the impulse. And the impulse can be described in two ways. It could be the force multiplied by the difference in time, or it could be the mass of the object times the final velocity minus the mass times the initial velocity. Now, we don't worry about this term too much because he's starting from a standstill and our initial velocity was 0. But we have all these, and now we can solve for the force to see what he hits with, and see if he breaks the bone. So to rearrange this equation, we would have F equals mv final over the delta time, or change in time, which now we just have to plug in our numbers, which is 96 kilograms for his mass. And the final velocity we just solved for was 14.11 meters per second over the change in time, which was 0.4 seconds. And this gives you a final reading of 3,388.5 newtons. Now, we looked up online. The amount of force needed to break a rib was about 3,300. To break a femur, it's about 4,000. Now the ribs are very plate-like and flat, so therefore that's why they're much easier to break than your femur. But the ankles in your bone are smaller, shorter, fatter, thicker. So we figured that this number would not have broken any bones in his ankle, but would have sustained an ankle sprain, which he would not have been able to walk off. And that is our conclusion.